Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to time response analysis of control systems. In this video we're going to discuss about another question where it has been given that the open loop transfer function of a unity feedback control system is given by this. Okay, and here we have to determine the parameters such as damping ratio, undamped natural frequency, damped frequency, damping parameter, and the peak overshoot value. Okay, so we know that the general format of a second order system closed loop, it is expressed as this: Gs by 1 plus Gs Hs is equal to omega n square by s square plus 2 zeta omega n s plus omega n square. So here if we do that with this Gs by 1 plus Gs Hs, it is 25 by s into s plus 5 by 1 plus Gs Hs, unity feedback, that means Hs is equal to 1. Okay, so it is similarly 125 by s into s plus 5, no need to mention 1 here, so it will be that. So it is 25 by s into s plus 5 divided by s into s plus 5 plus 25 by s into s plus 5. These two get cancelled out and it simply becomes 25 by s square plus 5s plus 25. So if we write this here, 25 by s square plus 5s plus 25, it is similar to this format here. See, it is similar. So it is the second order system, and here from this denominator, okay, which is called as the characteristic equation, 1 plus Gs Hs is equal to s square plus 2 zeta omega n s plus omega n square equal to 0, which is called as the characteristic equation. We have to determine the values of the undamped natural frequency omega n and the damping ratio. Okay, so here if we compare this denominator with this, okay, let me use a different ink, this equation with this, omega n square will be equal to 25. That implies omega n will be equal to plus 5 radians second. This. Then 2 zeta omega n will be equal to 5. 2 zeta omega n will be equal to 5. That implies zeta will be equal to 5 by 2 omega n, which is equal to 5 by 2 into 5, which is equal to 1 by 2, which is equal to 0.5. So the damping ratio zeta is equal to 0.5. Then we have to determine the damping factor, okay, which is equal to zeta omega n. Zeta omega n is simply zeta 0.5 into undamped natural frequency omega n, which is equal to 2.5. okay, then we have to determine the damped frequency of oscillation omega d, which is equal to omega n into root over of 1 minus zeta square. So it will be simply equal to omega n, which is equal to 5 into root over of 1 minus 0.5 square. So if we calculate it, it is coming around 4.6 4.33 radians per second. It is coming around 4.33 radians per second. That is the damped frequency of oscillations. The next parameter which we have to calculate is the peak overshoot. Okay, so peak overshoot, it is expressed in terms of percentage, which is equal to e to the power minus pi zeta by root over of 1 minus zeta square into 100. So it is equal to e to the power minus 3.14 into zeta, which is equal to 0.5 by root over of 1 minus 0.5 square into 100. That is coming around, it is coming around 0.1631 into 100 is equal to 16.31 percentage. That is the percentage overshoot. Okay, so what these parameters are: percentage overshoot, damping ratio, the damped frequency of oscillation, the undamped natural frequency of oscillations. I've already explained in detail in all the videos related to time domain analysis or time response analysis of zero order, first order and second order systems. Then for second order systems, we have discussed all the time response parameters in detail separately. So please watch those videos. And also I have discussed in detail about transfer function. Okay, so that there is no confusion in your mind about what is open loop transfer function, what is closed loop transfer function, what is forward path, what is feedback path, what is the forward path transfer function, feedback path transfer function, all that. Okay, so here this is the third question on time response analysis, evaluating the time response parameters.